Hi folks, welcome back. We're looking at rail car type problems in physics. Basically, a rail car type problem is when you have multiple objects or multiple masses that are attached by ropes and being pulled, or maybe they're all connected together or slammed together and being pushed on one side. Either way, it's basically a group of masses that are having a force applied to them. Now, often these problems want you to investigate what's going on with one particular object instead of the whole thing. So in this case, we want to know how much tension is acting on this last block that's being pulled by this person in the front, and all of the blocks are being pulled by the person in the front. Now, in order to do this, we need to simplify things. And the first simplification we could do comes from recognizing that the ropes really only act to connect the blocks. They really don't provide any aspect of motion changing. So they're basically just attached from one to the other. Now, it's true that this block is being pulled by this block because of that rope, but we could just get rid of it and call it an internal force that's happening between all the blocks. And if we do that, if we get rid of them and just kind of slid all the blocks together so they attach where the rope is, we have a new thing. This thing's called the system. We could treat all three blocks like they're only one object, and as a result, we can do some calculations. Now, first of all, you'll notice that we could do a free body diagram of this system. Now, it turns out all the masses times g would give us the weight of this system, and any support force from the horizontal surface would be the normal force acting on our system. And anything going on with the surfaces would result in a frictional force on our system. And now the applied force is the force that the person's applying in the front. Now what we could do from this point is we could do the sum of forces. Now the sum of forces in the y direction, or the vertical direction, well, that's just normal force minus the weight, and that equals 0. Nothing very interesting there. We could then look at the applied, or the sum of forces in the x direction, or horizontal direction. Now I'm going to choose that the right side is positive. So Fa minus F sub F, or the force of friction, equals mass times the acceleration. Now it's not just mass, it's mass of the system times the acceleration of the system. Now this last equation is going to be very important for us, because with this equation we can determine the acceleration of our system. Now this is important for us because it turns out every block that's connected is accelerating at the exact same rate. Not one of these blocks can accelerate differently from the other blocks because they're a part of a system. So that's a very key point to understand now. The acceleration of the system is the acceleration of each and every part of the system. That's important, and so we're going to use that. Now how we're going to use it is we're going to take a look at this first block, this block on the end that we want to know the tension that's acting on it. In order to do that, we need to just look at it only. So forget the system. Let's look at the part now. Now to do this, we want to do the sum of forces on this part. Now understand the frictional force we're talking about here is for this part. The normal force is for just this part, because it's caused by the weight of this part. Now the tension is the force that's being applied by the rope that's attached. So we could take this and write a sum of forces. And again, the vertical parts give us 0. So the sum of forces vertically just gives us 0. But the sum of forces horizontally, they don't equal 0. In fact, it's tension minus the force of friction equals mass of the part times the acceleration of that part, which is the acceleration of the system. So the information that we found out earlier we can use to solve for the net force horizontally, which means we can solve for the tension. Now, tension is equal to the mass times the acceleration of the system, and the mass we're talking about of the part, plus that frictional force on that part. That's how you would find the tension on that rope. Now, finding the other parts you could do, but we're just looking at this one part and seeing how you go about doing it. There's an overall pattern. Now here's some steps to go about doing it. First step, treat the system as an object composed of all the masses, meaning one object. Create a sum of forces acting externally on that system or that object. Solve for the acceleration of the system. Once you've done that, you can go back and draw a free body diagram for your part. Then you can create a sum of forces that are acting externally to that part. Remember, the rope is external to this part, but it's internal to the system. Then you can actually use the acceleration of the system that you found in part 3 to then use that with a sum of force equation to find missing information, such as the tension on the rope. Now, we need to look at this a little more simplistically so you know the pattern easily. And here it goes. The free body diagram of the system, then the sum of forces of the system from the free body diagram of the system, we could use that to find the acceleration of the system. Now, if we look at the part, we could do a free body diagram of the part, and then write a sum of forces of the part using the acceleration of the system. From that, we can then find the missing answer we're looking for, whether it be tension or whatever it may be. This is how you take on a multi-body system. Remember, there's a pattern, and this is it. Free body diagram of the system, sum of forces of the system to find the acceleration of the system. Free body diagram of the part, sum of forces of the part using the acceleration of the system to find our answer. This is how you run about doing these more complicated multi-body systems. Anyway, that's it. We'll be looking at the Atwood's machine in a later video, and that's basically just a two-mass system hung over a pulley. So, see you then.